The satellite is being used as one of the tool or as one of the platform for remote sensing. We need to know some basics of satellite. So satellites are natural satellites and man-made satellites. So what this satellite does is that the satellites will revolve around an object which is having a much higher mass than them. So the path followed by a satellite is referred to as an orbit. An object in the orbit is always called as a satellite. So man-made satellites are INSAT, Intelsat, Sputnik, and so many. So which are being deployed in space, which is present from the Earth's surface of about 36,000 kilometers. So from the surface of the Earth above, when we see, it will be about approximately 36,000 kilometers from the space. From there, we'll be launching our satellites. And there is a natural satellite also for Earth, which we call it as Moon. Then the Moon goes in the orbit around the Earth naturally with the centrifugal forces. The satellite orbits are matched to the capability and objective of the sensors that they carry. So depending upon the application, the satellite orbits will be revolving. Then the orbit selection will vary in terms of altitude and their orientation and rotation with respect to the Earth's rotation. So depending upon the Earth's rotation, the satellite orbits will be placed. Its speed, velocity, its positioning will vary. Positioning will vary depending upon the Earth's rotation. Here are the examples. The Moon revolves around the Earth, which is a natural satellite. A satellite launched by man around any planet for our purpose is called as an artificial satellite or a man-made satellite. Examples are Sputnik, Explorer, GSAT-1, GSAT-2, INSAT-1, INSAT-2, INSAT-2A, INSAT-2A, INSAT-2F, INSAT-2R are all examples of artificial satellites. These satellites provide a great deal of remote sensing imagery commonly used today. So the path followed by a satellite is always referred to as its orbits. The satellite orbits are matched to the capability and objective of the satellite sensors that they carry. So this is an orbit. You can see a diagram, schematic showing different types of orbits. Various orbits are possible depending upon inclination of the orbital plane, with the plane containing the Earth's equator. You can see at the center, we have the Earth's equator. In the center, we have the Earth's equator. At the right hand side, we have the east. In the left hand side, we have west. At the top, we have north. At the bottom, we have south. So if satellites are placed, which is revolving from north to south, you can see this direction, north to south, we call it as polar. The satellites are placed in this orbit, which revolves from north to south or south to north. North to south is called as polar orbit. Whereas when a satellite is placed in an orbit which is moving from east to west, you can see the direction east to west, or along the equator, which tracks the equator, is called as equatorial orbit. Equatorial orbit. So other than the polar and the equatorial orbits, if the orbit is placed, or if the satellite is placed in an orbit which is other than the polar and equatorial, is called as inclined in any direction, that tends to revolve around the Earth's surface. We call it as inclined orbits. So depending upon the application and need, we need to install, or we need to choose which orbit we want to put our satellite into space. So this is an example of an orbit. Orbit is a regular repeating path that one object in space takes around another. You can see sun is an object in space. The earth is revolving around the sun, and moon is another satellite or an object which is revolving around the earth, which acts as an object to that. And the object in an orbit is always called as a satellite. A satellite can be natural, like earth to the sun and moon to the earth. So orbital patterns. As already discussed, the path followed by a satellite is referred to as its orbit. The orbit selection can vary in terms of altitude, their orientation and rotation relative to the earth, whereas we will be defining the geostationary orbits. So the geostationary orbits will be placed at a very high altitudes of approximately 36,000 kilometers, as I said just now, revolving at the revolving at a speed which is equal to the rotation of the earth. So that type of satellites that are placed in geostationary orbits are called as geostationary satellites, and these are being used for weather and communication satellites. Weather and communication. Next is the near polar orbits. So these near polar orbits have an inclination almost parallel to a line running between the North Pole and the South Pole. And many of such of these orbits are called as sun synchronous orbits. That is, they cover each area at a constant local time of the day. They cover each area. You can see the diagram, and Earth is there. The satellite is rotating from north to south. Next is the ascending and descending passes. The satellites that are placed in the near polar orbits travel northwards on one side of the Earth and southwards on the second half of its orbit. Like this, as shown in the diagram. So you can see at the above diagram left hand side, the Earth is present. The satellites which moves towards northwards on one side of the Earth is called as ascending pass, and on the second half, the satellites will move on the second half of its orbit like this, which we call as descending pass. That you can see in pink color direction. The direction from top to bottom or from northwards is ascending pass, and from southwards it is descending pass. Then swath, you can see the area of the image on the Earth that is covered by the satellite. So swath is the area imaged on the surface. Because the Earth is rotating, the satellite swath that covers a new area with each consecutive passes. The satellite's orbit and the Earth rotation work together to allow complete coverage of the Earth. So that area which is being covered is your swath. You can see an apparent movement of this satellite swath. An orbit cycle will be completed when the satellite retraces its path, either from ascending path or either from the descending path. So during this orbiting, there could be an overlapping of the adjacent swaths. So the areas at higher altitude will be imaged more frequently than the equatorial zones. As you can see in the diagrams, the right hand side, both the diagrams. So the yellowish structure is your swath paths. And in this, we have to define an important concept called revisit period, which is the interval time required for the satellite to complete its orbit cycle interval time required for the satellite to complete its orbit cycle is to be considered, so such that it can retrace its path easily. Then we have to define the three parameters which are important in the orbiting of a satellite. One is apogee, second one perigee, third one inclination. Apogee, it is a point on the orbit where the distance of the satellite from the Earth's surface is maximum. You can see in the center we have the Earth, and the satellite revolves around the Earth. In some places, the satellite which is placed in the orbit will revolve near to the Earth's surface, which we call as the perigee point. And in some cases, the satellite will be present far away from the Earth's surface, which we call as apogee. So the point where the maximum distance between the Earth's surface and the satellite occurs is called as apogee, and the point where the Earth's surface and the satellite is minimum is called as perigee. Apogee, farthest point; perigee, the nearest point. Then inclination, the angle between the plane of orbit and the plane of equator. You can see plane of equator is the equatorial plane which is present along the equator of the Earth's surface. So that and the placement of a satellite, in which orbit we place. So that will create an angle in between them. So that angle we call as inclination angle. The angle between the plane of orbit of the satellite and plane of equator of the Earth is called as inclination of orbit. So next is the synchronous orbits. A synchronous orbit, it is an orbit where the orbital period equals the rotation rate of the orbited body. That is, an orbiting body which is a satellite will have a period equal to the average rotational period of the body, and with the same direction of rotation of that. Means, what are the satellite, in which direction it rotates, in which time period it rotates, that will be equal to the time period and rotation period of the satellite also. The rotation period of Earth will be equal to the rotation period of the satellite which is present in that particular orbit. So that type of orbit we call it as synchronous orbit. Okay, synchronous orbit, you can see 24 hours and 12 hours. After 24 hours, where is the satellite? After 12 hours, where is the satellite? If both are in sequence, then we call it as that the satellites are placed in synchronous orbits. So the synchronous orbit is where the satellite has a period equal to the average rotational period of the planet. So this we call it as synchronous orbits. In synchronous types, we have two different types of orbits. One is sun synchronous, another one geostationary. So already we had seen the geostationary. Is that the geostationary orbits are the orbits that revolve around the Earth with a orbital period matching the Earth's rotational period. So it lies in the equatorial plane around the Earth. So a satellite in such an orbit will be having an approximate altitude of about 36,000 kilometers. So this we call as geostationary orbits. And next we have the sun synchronous orbits. So where the orbit which combines altitude and inclination in such a way that the satellite passes over any given point of the Earth's surface at the same local solar time. So the orbit of sun synchronous will be around 700 to 800 kilometers over the surface of the Earth and with same orientation. Okay. Till now, any queries you can type in chat box. Then I'll proceed further for polar, sun synchronous, and geosynchronous again. Any queries? Type in chat box. Since there are no queries, I proceed further on to the next topic. The topic is types of orbits: solar, sun synchronous, and geosynchronous. So polar orbits will have inclination of about 90 degrees, which allows the satellites to see virtually very part of the Earth. So this takes approximately 90 minutes for the satellite to complete one orbit. So these satellites have many uses, such as measuring ozone concentration in the stratosphere, and measuring the temperatures in the different atmospheres. For that, we can use the near polar orbits, measuring the contents of O3s or ozones. So sun synchronous, these orbits allows a satellite to pass over a section of the Earth at the same time of day. You can see an example of sun synchronous daytime. So these satellites orbit at an altitude of between 700 to 800 kilometers from the surface of the Earth. These orbits are used for satellites that need a constant amount of sunlight. So sunlight is required for this. So the satellites takes pictures of the Earth that are best during bright sunlight. So this we call it as sun synchronous. You can see the example. The relativistic diagram. We have the Earth, and surrounding that we have a sun synchronous satellite. During daytime, we can measure the Earth's information inclined at an orbit. The inclination is about 98.2 degrees of the satellite, which has an orbital period of approximately 98.9 minutes, which is used for ground tracking. The time of day, which is measured, is between 9:45 a.m. local time. The altitude is around 705 kilometers, where the satellite is deployed. Diagram showing the orbit of sun synchronous satellite. Next is the geosynchronous. This is also called as geostationary orbits. So the satellites in these orbits rotate the Earth at the same rate as the Earth spins. So these are used largely to study hurricanes or cyclones in different regions, which are also used for communication satellites. The disadvantage in the geosynchronous is that near the poles, it is very difficult to track the information from the geosynchronous satellites. So for that, we'll be using polar. So these are placed about 36,000 kilometers from the Earth's surface. The satellite is an object which put it in an orbit around the Earth or any other planet in order to relay communication signals or transmit scientific data. You can see sun in the center, yellow color. An orbit around the sun is Earth is revolving, and revolving the Earth is a satellite. It is our artificial or man-made satellites. Example of geosynchronous satellites. You can see the solar panels in violet color. Black is your space. The white dots are your stars and galaxies in the Milky Way galaxy. We have the transponders, we have the antennas, we have the satellite system in space, so which is used for weather forecasting, satellite television, satellite radio, etc. So the geosynchronous orbit is an orbit that revolves around the Earth with an orbital period of about 1 sidereal day, which matches the Earth's sidereal day, which is about 23 hours, 5 minutes, and 4.9 seconds. You can see Earth at the center in this diagram of the picture. We have geostationary, and at an angle of inclination, we have a geosynchronous orbits. The synchronization of rotation and orbital period means that for any observer on the surface of the Earth, the object is in geosynchronous orbit that returns to exactly the same position in the sky after a period of one sidereal day. So today, if you are viewing a satellite which is present at the top of your head, the next day at the same time when you see, the same satellite will be present if you are able to visualize. So that is the meaning. What is present inside a geostationary satellite, which we had seen? We have the solar panel or the solar arrays at both the ends of the satellite, which acts as a wings. Then we have a battery module, a satellite house. We have a C-band antenna. We are having a fuel tank. We are having a gas thruster. So one solar panel will point towards the north and another one towards south. Then we have the earth or sun sensors depending upon the application. We have omnidirectional antennas. Then we have the KU band feed horn antenna and the KU band antenna. This is just a pictorial representation of geostationary satellite which is deployed in space. And the sun synchronous. These satellites are used for military purposes and especially in remote sensing. Landsat, QuickBird, etc. are the example of satellites of sun synchronous, where they are located approximately 750 kilometers above the surface of the Earth. These satellites move around the Earth and always gets its power source from the sun itself. You can see the sun synchronous revolves around the sun with respect to different seasons: winter season, spring season, summer season, autumn season, and gives information to the Earth. So the rate is equal to the average rate of Earth's rotation around the sun. The position of sun relative to orbital plane remains relatively constant. The sun synchronous orbits can be achieved around other central bodies, usually at 90-degree inclinations. Next is an example of the sun synchronous orbit, how it is being placed, what are its orbits. There are low Earth orbiting LEO, where the altitude of this LEO satellites are about 600 to 1,000 kilometers from the surface of the Earth. The equatorial crossing time would be the local apparent solar time when the satellite crosses the equator. Then we have the ascending orbit. The satellite is moving south to north. From south, it moves towards the north when the portion of the orbit tracks crosses the equator. So that is ascending orbit. Descending orbit is that the satellite is moving north to south when that portion of the orbit track crosses the equator. So till that descending orbit. Then period is that a typical polar sun synchronous low Earth orbiting satellite takes about 90 minutes to complete the entire Earth, to circle the entire Earth. So this gives per day 16 orbiting. So this we call it as a sun synchronous satellite. So establishing an orbit types. depends upon geo, LEO, transfer point, parking point, temporary orbit for satellite operational takes, establishment of orbital selection, and so many. So orbit selection, orbit design process, the financial budget, launch, the Earth coverage of that particular orbit, constellation design, basic formation, station keeping, collision avoidance is a major factor in the design. So the orbital design process starts with the altitude selection, resolution. Lower altitude is better for high solution. For swath width, higher altitude is better. Then we have to see inclination. That ground station coverage is to be considered. The lifetime of the satellite is to be designed, and the survivability of that particular satellite is to be considered in ambient environments also. So this is the Earth coverage as an example of a small orbit with the ascending as well as the descending. You can see a wave structure. So any doubts till this? Right. If you have any doubts, you can type in chat box. Then I'll proceed further on to the next topic called different types of satellites. Orbiting topic is over. Different types of orbiting is over. Next, I am going to start about satellites used for different purposes. So any doubts, you can type in chat box. Then we'll proceed further. So 5 to 10 minutes time is given for query session. I think this slide will give you the difference between geostationary and geosynchronous. Sai Ganesh, you can see this slide. Geostationary and geosynchronous both resemble the same terms in terms of satellite, where the rotation of the satellite in space will have the same rate as that of the Earth, which we call it as geostationary and or geosynchronous. There is no difference at all. Both would be same. As corresponding to Earth only. Since we are measuring only the Earth's atmosphere or Earth's information for remote sensing, if it is only Earth, geostationary and geosynchronous are same. The satellite which is revolving around that particular orbit in space, if that rotates with the same rate as that of Earth, we call it as geosynchronous or geostationary. Both are same. Okay, understood? Any other queries you can type in chat box. since there are no queries, I further proceed on to the next topic, Earth resource satellites. So you would have seen this diagram in the earlier classes also, where A, B, C, D, E, F, G are present. A is the source or illumination, which acts as energy, ultraviolet wave radiation. B is the radiation in the atmosphere. C is the interaction with the target. D is the recording energy. E is the transmission, perception, processing. F is your interpretation analysis. G is the application or the user who requires this. So in this, the work of this Earth resource satellites is of recording. So that is what it is highlighted in D. Highlighted as in color, okay, red color, which is D. So the function of the Earth resource satellite is in D, recording the data of the particular object or the target that we want to do. So an orbiting platform containing imaging equipment gathers data from a specified section of the Earth and transmits the data to an earthbound receiving station. So this is where the Earth resource satellites have been deployed. So Earth resource satellites have the mission to monitor Earth's oceans, ice caps, water bodies, coastal regions, etc. They do that. They provide systematic, repetitive global measurements of wind, direction, the waves height, surface temperature, surface altitude, cloud coverage, atmospheric water vapor level, speed of the wind blowing in which direction. So the cyclones, hurricanes can be easily determined or easily measured at what distance, in which place the hurricane or the cyclone is present by using this Earth resource satellite easily, which monitors Earth's water bodies majorly. Next is the meteorological satellites or the weather satellites. So this satellites is a specific satellite which is used to monitor only the weather and climate changes of the Earth. So there are two types of satellites being deployed for meteorological surveying or the climate monitoring. One is the polar orbiting and the geosynchronous or the geostationary orbiting. So the polar orbiting, as we are familiar, passes approximately over the poles, North Pole and South Pole, of about 700 to 800 kilometers, where the whole satellite will cover it by 16 times per day. And the examples are OceanSat-1, IRS, NOAA are being deployed in polar orbiting. Whereas in geostationary orbiting, satellite orbits around the world over the equator at a height of 36,000 kilometers, which can complete one orbit or one complete revolution in 24 hours synchronization with the Earth's rotation about its own axis. And thus they remain over the same location on the equator. Examples are GOES, INSAT, METEOSAT are the examples of geostationary meteorological satellites. Just now we had seen NOAA, which is polar orbiting satellite. So NOAA is abbreviated as National Oceanic Atmospheric Administration. So which uses the following meteorological payloads. One is Advanced Very High Resolution Radiometer, AVHRR. So this radar is being used in NOAA satellites in polar orbiting for weather monitoring. So here the data are acquired with the field scanner that enables a global coverage on a daily basis every day with a ground resolution of 1.1 kilometer at Nadir Point. Nadir Point is the point where the satellite and the sun meets with the Earth beneath that, beneath the satellite. We measure it. The sensor also provides a data stream of nominal 4 km resolution that is achieved by sampling and averaging the full resolution of 1.1 kilometer data on board the satellite. So we'll see what is this resolution is, what is this nominal resolution in the further classes. Okay, we'll not bother about that. We'll see what is this resolution is. Okay. We have another meteorological payload, which is TRIOS, operational vertical sounder, so which we shortly write as TOVS. So the TOVS incorporates a high resolution infrared radiation sounder, so which has an atmospheric radiation of 20 infrared channels and is primarily used to obtain the vertical temperature and moisture distribution in the troposphere. So the temperature and moisture contents in the troposphere can be easily absorbed by this TOVS. TRIOS, operational vertical sounder, will detect these changes easily in troposphere. Then we have the ERB, Earth's radiation budget. The atmospheric motion is driven by differential absorption of solar radiation and infrared loss to space. So the study of this atmospheric motion of absorption was done by the Earth's radiation budget. So you can see some of the specifications, some of the bands, or we call it as wavelengths, in what resolution it can be used, in what altitude. For example, if you use a NOAA, the band is 1, 2, 3, 4, 5 classified, depending upon the wavelength, 0.58 to 0.68 micrometer. In band 2, 0.725 to 1.10 micrometer. In band 3, 3.55 to 3.93 micrometer. In band 4, 10.3 to 11.3 micrometer. In band 5, 11.5 to 12.5 micrometer. For all this, we had a swath width of approximately 2400 with a spatial resolution of 1.1 kilometer. So from the satellite, the resolution was acquired for 1.1 kilometer from the surface of the Earth with a daily repetition average. The orbit was kept at 833 kilometers. You can see the NOAA AVHRR. NOAA used advanced very high resolution radiometer of Tornado in the year 2001, June 18th at 6:59 morning. So using visible spectrum is the first right hand side, you can see visible spectrum, the visible region, and then using same at thermal infrared region, you can see how the same is being classified. So clouds which are being formed and how it appears in thermal infrared. So this left hand side is a completely separate ocean surface temperature measurements. Violet, blue, green, yellow, orange, all those things. Depending upon the variations, you can find what are these. Next is the GOES, Geostationary Operational Environmental Satellite. GOES, Geostationary Operational Environmental Satellite, was designed by the NASA, where two GOES satellites placed in geostationary orbits of approximately 36,000 kilometers above the equator, each viewing approximately one third of the Earth. So one is situated at 75-degree west longitude and monitors North and South America and most of the Atlantic Ocean, whereas the other, which is situated at 135-degree west longitude and monitors North America and the Pacific Ocean. So together they cover the region from 20 degree west to 165-degree east longitude. GOES. So there are two generations of GOES satellites being launched, which measures emitted and reflected radiation from which atmospheric temperature, winds, moisture, and cloud cover can be derived. The first generation consisted of GOES 1, launched in 1975, through GOES 7, launched in 1992. During their design, the satellites were capable of viewing the Earth only a small percentage of time. Approximately 5% of time was being viewed. So then, in the second generation of satellites, which began with GOES 8, launched in 1994, had numerous technological improvements over the first series. The drawbacks in the first generation were overcome in the second, where mostly 80% were being covered. You can see the coverage of North America and South America by these satellites. The satellite was deployed in space for covering both. The photograph was taken on August 2005 at 5:45. You can see the resemblance of that. How the North America looks, the first picture, in the second picture, and in the third picture. Next is GOES geostationary operational environmental satellite and the METOSAT, meteorological satellite. You can see an island. Above the island, there is a formation of clouds, which represents there is an formation of cyclone or a hurricane in that particular region. Next is the deployment of sensors. Before we proceed on to the sensors, if there is any queries, you can type in chat box. Yeah, since there are no further queries, we move on to the next topic, which is on sensor platforms. So these four are and best examples of sensors of sensors that are used for remote sensing. The first one is the ground-based sensors. We have a truck which is having an antenna which will capture information of a remote location. You can see a farther distance so that it can acquire without actually being going there. So ground-based sensor. Second is an aircraft which can take sensors which can acquire information during its travel. Another one is a space shuttle which can get data in space, information about the space. Then we have the satellites that revolves around the Earth or Sun, which will acquire its information and give it to the Earth station. Then all the sensors will have these four resolutions. One is spatial resolution, which relates to pixel size of the given coverage of the image. Spatial resolution. Second one is the spectral resolution, which determines the range of wavelengths recorded by that sensor. For example, the band's number, position, and width can be easily determined. Spectral bandwidth. Third one is the radiometric resolution, which has a range of integers that can be recorded by a sensor measured in binary computer codes. Radiometric resolution. Fourth one is the temporal resolution. So this temporal resolution is the time that elapses between the successive dates of acquiring the images. The temporal resolution is a function of the orbital parameters, orbital altitude, shape, and inclination, where the greater the altitude, the longer the orbital period. It is obtained with the acceleration of gravity. So let us see the spatial resolution first. So we have an aircraft. We have an aircraft which is positioned at the top of the Earth's surface. So we have the A, we have the B, we have the C as the distance. You can see the distance between the aircraft and the Earth surface is C. The curvature is A and the object is B. So spatial resolution refers to the size of a small feature that it can detect. So that depends upon the IFOV, which is instantaneous field of view. So this IFOV is an angular cone of visibility of the sensor that determines the area which is seen on the ground from a given altitude. So altitude is your C at a given instant of time. So this spatial resolution is a coarse resolution or a low resolution. You can see at the top picture we have an aircraft is capturing an image of a place. You can see at the top, which consists of large water bodies, smaller water bodies, streets, aerodromes, which gives us a low resolution. So the same picture, some part I had zoomed in or I had given for a higher resolution, which shows how many larger buildings are present. You can see this, which I am pointing, is of larger buildings interconnected. This is your road. This is asphalt road. This is your road. This is your road. These are small buildings, small houses which are being built. So this gives you a spatial resolution definition. That depends upon the IFOV. Finally, the remotely sensed data are acquired by a sensor system which collects data with the same IFOV on each date. For example, Landsat data, which is collected at the 30 cross 30 meter spatial resolution on 2 dates, on different dates, could be relatively easier to register one or the other. So the performance change detection using the data collected from the 2 different sensors with 2 different IFOVs can also be visualized. So we need to decide on which one is the best to record it, whether the first date or the second date or the first one or the second date. So here is a series of information in 5 different layers. Okay. Remotely sensed data used for change detection should be geometrically rectified if there is a geometrical error. Misregistration of two images may result in the identification of false change between the data sets. So everything is recorded with respect to dates. Day 1, day 2, day 3, day 4, day 5, or date 1, day 2, date 3, date 4, date 5, date 5. For example, just one pixel misregistration may cause a stable road on the two dates to show up a new road in the changed image. So that has to be carefully drawn. So where the pixel geometry comes into play. So here is the place where we use the optical pixel wavelength or the optical pixel width to find the exact geometry which is detected by the sensors. So we have an area that is being imaged by the sensor as A, but in some places these gets overlapped where the overlapping pixels are scaled to match a geometrical pixel size B. You can see in this left hand side diagram. So A's are being overlapped. So the exact resolution is being produced by geometrical pixel size B. So an effect of the scale angle in aircraft imaginary is your panoramic distortion, which you can see in A, and the resulting image distortion in B. You can see A and B. So the panoramic distortion has pixel width increased away from a vertical view, whereas in the resulting image distortion, image features have lateral distortion when displayed with a constant pixel width. It is in B. Next, we are going to see the image distortion. Now, the images that are being photographed or taken can be distorted. A is an airborne image, raw or rectified. You can see a raw image is A. A photograph is taken by the aircraft or any satellite that is being sent. It is being rectified as B. So this portion is being extracted. It is being view enhanced. And a C shows the visualization deformation of a surface feature. So C is extracted again from B. So it shows two different regions. One is a roofy regions where RCC concrete may be put up, and another one is a grassy region. So this becomes the ground truth region, which is C. Then IFOVs prints over the simulated ground image showing the real distribution of the measurements. You can see each and every of C is being divided into like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So where the exact roofing can be classified. How much pixels are being used for roofing, how much pixels are grass is present. So then further enhancement we get this. So after the spatial resolution, we are going to see the spectral resolution. The spectral resolution describes the ability of a sensor to define wavelength intervals. Many remote sensing systems record energy over the several separate wavelength ranges at various spectral resolutions. Here we can use a multispectral or a hyperspectral sensors or a field spectrometers, depending upon the satellite or depending upon the resolution or application being required. So we can use it for water, clear water. We can use it for a turbid water. We can use it for wet soil, dry soil, or vegetation, or anything. So ideally, the same sensor system is used to acquire imaginary on multiple dates. For multiple sensor, we use select banding option that approximates one sensor with another sensor. So for example, Landsat MSS, Mobile Satellite Service Band, uses 4 green, 5 red, and 7 infrared bands. And spot bands use green, red, near infrared, whereas the Landsat ETM uses band 2, band 3, band 4 for green, red, and near infrared regions for obtaining the spectral resolutions. This is an example of a field spectrometer. You are having a processing unit. You can see this is a processing unit, a sensor, which acquires information, and a display unit of graph. So that graph is elaborated here. Okay, here is the person who is carrying that. Now to measure soil strength. Next is the radiometric resolution. So this relates to the energy difference between which it determines different radiation, which is brightness level in an image. You can see the first picture. There is a 2-bit data or 2-level radiometric resolution. You can see a photograph is taken with 1-bit data. The same is taken with 2-bit data, which is 4-level. Okay, 2 power 2, 4-level. So next, compare this with the 6-bit data, which is 2 power 6. 2 power 6, you get a more resolution. So this we call as radiometric resolution. So levels are restored as binary numbers in a computer. So 2-level, 4-level, 64-level. From this you can identify which gives us the best radiometric resolution for a specified area. So the radiometric resolution is that the sensors collects the data, the same radiometric precision on both the dates. When the radiometric resolution of data acquired by one system is compared with the data acquired by higher radiometric resolution instruments like Landsat TM, Landsat MSS1, Landsat 8-bit data, then they should be decompressed to 8 bits for change in detection purposes. So the brightness values associated with both the dates of imagery are converted to apparent surface reflectance, which eliminates this problem. The last one is the last resolution is your temporal resolution. So temporal resolution refers to the length of a time that it takes for a satellite to complete one orbit cycle. So the absolute temporal resolution of a remote sensing system is to image the exact same area at the same viewing angle a second time, that is equal to orbit cycle time. However, because of some overlapping in the image, Schwartz and off-nadir pointing capability will occur that will make the system to revisit again, which we call it as actual temporal resolution. This temporal resolution should be done or is held constantly during changing the detection. For example, if you are observing, you are having an remote sensing data to be observed on dates February 1, 2005 and February 1, 2011. The anniversary date imagery minimizes the influence of the seasonal, sun angle, and plant phenological differences that can negatively impact a change in the detection. So during the changes, the temporal resolution plays a major part in obtaining the data acquisition of a remote sensing system. So next is the scanners. We have 2 different types of scanners, which gets the data from the scanner and gives it to the processing unit, and further recording can be done. So one is the across track scanning, And second one, along track scanning. Across track scanning will scan the surface in a series of lines, whereas along track scanners uses a linear array of detectors that are pushed along the flight track